So today we'll have a third lecture of Sergei. So quantum topology at generic Q, please.
All right, so as usual, I'll share the link to the whiteboard. You can either try to follow it on screen. So let's see if I can share it. Here we go. Or independently look at various places. So I decided I'll just continue with the same whiteboard, in part because makes it very convenient to refer to some previous statements. So we already used it, or I used it last time, to point back by scrolling back and forth. So maybe I'll just stick with this for now. So we're in lecture 3, and lectures 1 and 2 were heavily rooted in combinatorics and topology. So we'll slowly be transitioning to slightly more advanced material. I hope it won't cause any difficulties, because in the first 2 lectures, I really tried to be extremely elementary, basically focusing on combinatorics and simpler topological constructions. But of course, sooner or later, we'll have to advance a little further. And again, I'll still try to make it pedagogical and clarify conceptual points, so we'll be shifting from maybe concrete to conceptual in this remaining 2 lectures. But again, as usual, feel free to interrupt me, ask any questions. They're always extremely welcome, or make suggestions. And I'm already trying to accommodate some of the suggestions from previous times. So first, call of order that we need to do is to generalize the construction slightly. It's the last perhaps thing that we'll do in topology, at least in this part of the lectures, unless there are more requests. So first, I'll give you a definition that comes from joint work with Ciprian Manolescu, which basically generalizes that combinatorial or simple plumbing construction to a more general manifold. So it's a surgery formula. Since we learned that any closed oriented 3 manifold can be constructed by surgeries on knots and links, we can use this construction of 3 manifolds to produce analogous construction of 3 manifold invariants. So for this, we need this formula, to which I'll refer as a surgery formula. And it has exactly the same structure as what we saw before, but now I can call things by their real name. So there's invariant of a 3 manifold, which I'll denote by M3. And again, it depends on Q, assumed to be generic complex number inside the unit disk, is going to be defined as multiple integral. So hopefully, again, by now I motivated much of this structure over as many variables as, so here we have a product over link components, dxi over 2 pi I xi, maybe let me call it j. As many integration variables as components of the link. There will be a certain integrand that depends on a choice of link k, that depends on all of these integration variables, and also possibly on variable q. And then we'll write a theta function analogous to what we had before, which depends on, in fact, same as what we had before, that depends on all of the variables and q. Let's see. My iPad is telling me that I'm still connecting, so I'm not sure if you can see the rest of the formula. Oh, it just disappeared, but it's only a small part. Here we go. So in this general formula, so let me move it up on the screen. There are basically two pieces, so two parts to remember. So the first part is exactly what we saw earlier. It involves the integral and theta function, and this is where the surgery coefficients enter. Surgery or framing data enters here. And then, so this part does not depend on the choice of link on which we do the surgery. And this is the rest of the formula, basically the integrand. So this encodes information about the link and is basically this invariant for S3 minus K. And once we close up all the toral boundaries on a link complement, that's precisely this operation of integration with a theta function. So in this approach, based on surgeries, the formulae, such surgery formulae are completely universal, but the question becomes how first we do construct this integrand Fk for, or that hat of a link complement for not and link complements. So let me give you an example, and later on I'll mention how to obtain this example using quantum groups at generic Q. But since I already told you about various pictures of knots, which I corrected overnight, and now they look even prettier. So for example, for figure 8 knot, you have the following result. So there is only one component. So there is only one variable x to worry about. And in this case, Fk of x and q has the following form. In fact, this form is fairly general for any knot. You have x to the power b, and then z hat b of S3 minus k, where this values, so that's again, this formula is general for any knot, but for specifically for figure 8 knot, you have z hat 1 is equal to 1. I'm just going to write non-zero values. Z hat 3 is equal to 2. Z hat 2 is 0. Z hat 5 is equal to 1 over q plus 3 plus q. Z hat 7, yeah.
Yeah, I am sure you can write many of them, but I mean, it does not explain anything. What is z hat of S3 minus k? Your M3 was closed without boundaries, so, and ZB was defined only for such three manifold. S3 minus k certainly is not in the class.
Right, so that's what I'm trying to say, that at some point now, to define it for general manifolds, I have to explain to you how to obtain, in the surgery approach, I have to explain how to obtain this z hat of S3 minus k for not and link complements, right? So that if we obtain that, then using this general surgery formula, you can produce it for closed manifolds. So surgery formula is meant to be a bridge between link and not complements and closed manifolds. So far I'm just explaining this part. I'll explain how to obtain it for not and link complements in the rest of the lecture. Does it make sense?
Yes, some sense. The only I just, as a mathematician, I objected to use of the notation z hat for something which did not belong to the class. It's it's something which is defined for the complement of the knot, and you want to call it z hat. Okay.
Exactly. Yeah. So far, it's just a name for coefficients. So I gave you a result, and again, I'll explain where it comes from. But I gave the name to coefficients, which is suggestive, so that I don't have to redefine it later on. So, but it's it just so far just a name. So again, this will come from. I'll show you how to get this from quantum group. A generic Q. So, but again, at this point, I'm trying to also maybe illustrate things showing that they're fairly concrete, explicit, and so on. And I apologize if I'm moving too slowly. So next statement I want to make is to rephrase what we had before in this language. So the following lemma, if M3 of the previous type, namely manifold constructed out of link, which consists only of various linked unknots, then this, what we had before, is precisely such instance of a surgery formula where fk of xq is, now it has many axes, of course, so as many as link components or vertices in a plumbing graph. And you can write it in a succinct form as product over xi minus 1 to the power 2 minus degree of the vertex I. And here a degree is the same as valency. It could be called many different names. It basically is number of edges which are coming into this given vertex. So that's the degree.
So it's, for me, it's a bit strange that you call a definition something which is a formula. Yeah, so it's kind of, such things cannot stand as definitions. It should be a formula for something. You know, it's too
Oh, no. What I'm saying,
to be a definition.
Sorry, why is it a definition? It's a
because
formula.
you wrote it as a definition. Surgery formula, it's a definition. According to you, ZB hat of M3 cube equal to this multiple integral.
Correct. Yes.
But it's, I mean, just nothing, but it's too complicated to be a definition.
Well, we want to define an object and then prove certain statements about its properties, its behavior, right? So, what is there a question about the definition? So I'll scroll back to, you're referring to this definition, right?
Yeah.
Well, it's a definition of an operation that takes something as an input and produces analogous invariant for closed three manifolds. So it's I mean, theorems would be statements about this formula.
Yeah, that it does not depend on the Kirby move or something.
Exactly, yeah. So then we had many bullet points, which were easy enough in the case of some class, but now, unfortunately, it's easier to make it as a definition and then independently start proving properties of this.
Okay.
Yeah. So then lemma here is a meaningful statement. It's a very small statement. So that's why I call it just a lemma, that what we had before is an instance of such formula where integrand is given by this succinct form. So it's just a simple exercise that you can rewrite what we had before in terms of product over edges and vertices as just product over vertices with this integrand. So. And the reason I want to give this lemma is I'll refer to it a couple of times. So that's an alternative form of writing the same expression as before. But I also want to give you an exercise or homework. I hope it's okay, since this is kind of mini lecture course, where I ask you to, in the context of this lemma, for this special case of steel plough manifolds with which we had by now enough experience. So I'm not going to do it in front of you, but I actually ask you to do it yourself, is first of all, consider the limit when q goes to 1. After all, if we have something that depends on q and is already invariant under Turby moves, you can substitute some special values. So q equals 1, of course, is not guaranteed to be a nice value, because I said that things are convergent inside the unit disk, so potentially they might be divergent and so on. That's why it's a non-trivial exercise. Otherwise, there would be nothing to do here. So I ask you to, first of all, play with this limit, explore it and see what you get, and also compare to the derived torsion.
Do we supposed to know what is derived torsion?
That's right. So either I'll actually tell you today some of it, and I'll give you enough information today, but also some of you who already know what derived torsion is can do it independently, but actually enough information will be in this lecture. And in particular, I'll give you sort of a hint or a solution to what to expect, but there is still something for you to do. Namely, the inverse of this object fk of xq, again for just planned manifolds, when you evaluate it at q equals 1.
Well, I'm sorry, your formula does not depend on q. Fk of xq.
Sorry. Yes, that's right. Absolutely right. Yes. Sorry, that I meant to say. Yes. Thank you so much. This is inverse of, in fact, z hat of b of q at q equals 1. So this gives derived torsion. And 1 over what I meant to say fk of x, indeed this does not depend on q in the first place, is derived torsion of link complement S3 minus k. And again, well, I'll give you enough information about derived torsion now. But the reason I wanted to state it in this way is I want to give you different flavors of what this kind of object that we constructed or we're exploring. And this exercise or homework gives me an opportunity to say first, make a first comment, or I'll call it corollary to this exercise, is that you can think of this object, this Q-series invariant that depends on a choice of 3 manifold and Q, as basically Q deformation of inverse derived torsion.
Yeah, it would be nice if all this exercise appeared after you gave a definition of derived torsion. Otherwise, for me, it's just nothing. I know derived, but I don't know what derived torsion is.
Yeah, so again, I will have to cut the corners in this for lectures, so I apologize if I won't give the full, complete definition of derived torsion, but like I said, I'll give you an idea today. So it will be enough to hopefully get you interested in trying to verify this exercise or homework. So for now, all you have to know is that derived torsion is yet another invariant of three manifolds, which depends on the same type of labels, and it doesn't depend on Q. In fact, you recover that, or the inverse of that, if you send Q to 1. So before I leave the world of plumbed manifolds, this special world, let me also try to shed light on the nature of this integrand and make another remark by asking the following question. Basically, you see that here, if you use f, you get z hat. If you use f inverse and set q to 1, you get derived torsion. So natural question is, are there other formulae? In other words, can we construct invariance under this Kirby-Neumann moves by using different choices of integrand? And here, see what's happening is we have basically the way I rewrote it using this lemma, we have integrand for each vertex. So could we come up with another function that depends on x and maybe q in such a way that result is invariant under Kirby moves? So surprisingly, this, so yeah, let me first formulate this as a question. So in other words, can we find other alternatives for this choice of integrand of xi minus xi inverse to the power 2 minus degree of the corresponding vertex, such that it's the result is invariant over three manifold, invariant under Kirby-Neumann moves. And the answer to this was surprisingly not known or not studied systematically until recently. And the answer was given in a fairly recent, in fact, a very recent paper of Rostislav Akhmedchet, Peter Johnson, and Slava Krushkal, where they say that the answer is yes, so there are alternatives. And in fact, they sort of classify them. So they claim that every function, or rather set of data that they call admissible, and I'll write the condition in the next line, admissible F and R. So admissible will appear in the next line. Does give invariant of a three manifold. So here F and R is a set of data which is labeled by N, that's non-negative integer, and R, which is any integer. And the admissible condition means that F of N plus 1, R plus 1, it's a very simple recursion relation, minus F of N plus 1, R minus 1 equals Fn of R. So that's the definition of what admissible data is. And claim is that any choice of such numbers, f of n of r, that satisfy this recursion relation, produces for you an invariant of Plum three manifold. And notice that this recursion in R is of step 2. Therefore, you actually have a lot of data, namely worth of natural numbers plus another set of natural numbers, which determine the initial stage of the recursion. You can think of this as for two particular values of r, say r equals 0 and r equals 1, which can be anything, and then recursion defines for you the rest of it. So it's actually a lot of invariants. And they didn't really study what kind of invariants you get in various cases, but they pointed out that these invariants include the suspects that we'll already either know or will know. So for example, Z hat, Turaev torsion, which is given by inverse version of this F torsion, and what they call the double hat, all appear as in this list. An interesting question, since this is again kind of a seminar or lectures supposed to introduce you to the subject. So I think there is a lot of potential to play with this admissible solutions and see what kind of invariants we get. So I'll put here a big question mark, indicating that I think it's an interesting direction for further research.
Are they all different, this kind of non-equivalent?
Yeah, that's a very good question. So it's not clear. At first, when I saw the result, I naively perhaps thought that they're all different. But after discussing it with colleagues, it's not entirely clear. I think that's a good, extremely good open question about this work. Yeah. All right. So now, as promised, all this plumbing and surgery formulae are out of the way. So my next two chapters, major chapters, involve a bit of discussion of counting. And so this will be less precise or technical or concrete, but maybe more conceptual. And then chapter after that will be quantum groups and geometry. By geometry, meaning geometry associated with quantum groups or geometric representation theory. So maybe most of that material will be in the next lecture, but in this next chapter, I want to talk about a little bit about counting.
Sergei, but again, confused. So it's a mathematical theorem that if you choose an admissible FNR, then you get something invariant with respect to Kirby moves. So this is a mathematically rigorous result.
Correct. Yes.
Okay.
Yeah. It's basically trying to ask what is so. When we were constructing this in the first lecture, I made very specific choices, and you quite rightly asked me what's so special about this ad hoc choice. So then my argument, once we finished the construction, was, look, it's satisfying Kirby moves. So what they ask is, suppose we want to construct something of this form in the form of such integrals. So what do we have other choices for? In other words, how big is the space of solutions satisfying the Kirby moves? So that's precisely the content.
Yeah, but so you see, since you cannot cross out the previous kind of 30 or something years, so there were other invariants. So you somehow, as a mathematician, I would of course kind of organize the lectures in a different way, because numbers at least tell me nothing. I am not a Ramanujan, and but the concepts can tell more. For example, either a topological 3D topological quantum field theory, which gives the Z hat as partition function, and how they are related to the invariants from 90s for which were obtained for roots of unities. Do they specialize in those or what?
Yeah, so maybe before talking about counting, then let me address or at least answer this question. So I think so first statement is that it's an expectation, or that I think that's correct way to formulate it is as a sort of challenge we know that, or we expect that z hat of B of M3, so that's another perspective that depends on Q, is first of all, it's spin to Q of T. So it depends on choice of spin structures and so on. Associated to UQ, in our case of SL2, but in general, it could be any root system. So that's not terribly important. But the challenge is to construct it fully. So what currently is known is, so TQFT is a very loaded statement. It may mean, for example, expanded TQFT. And you can ask then, what is a category associated to a circle? So that's not known. Also, TQFT means cutting and gluing over general two manifolds. So you can ask, what is, for example, a space of states along a two-dimensional surface? And it's known fully only in genus 1, which was one of the statements I made earlier. That's why I organized these lectures. I'm telling you what I know. But there are lots of things which are not known. For instance, for higher genus, it's known what the space is abstractly associated to Riemann surface of genus G, but it's not known how to how it implements the action of the mapping class group, how mapping class group acts on it. So there are many ingredients. So TQFT is extremely loaded statement. And until recently, actually, so this is also an example of decorated TQFT. As you can see, it's decorated by spin C structures. And even constructing some similar three-manifold invariants such as Turaev torsion, which are decorated in TQFT language, is quite non-trivial. So I wouldn't be able to do it in 4 lectures. I mean, I can in principle, but not in a short time allowed.
Yeah, but do you consider when you kind of add the nodes, will it be finite dimensional representations of UQ of G which you put on the nodes?
You can consider, because we're working at generic Q, you can consider, most natural thing is actually to consider infinite dimensional representation. So that I do plan to talk about later.
But your infinite dimensional will be of highest weight type, yeah?
Correct, yes. There are Verma modules of highest or lowest weight, that's correct. So therefore, the answer to the question TQFT, it's I don't know, and I think that's part of the reason to give these lectures, to propose that there is a lot of work that we would like to see in this area, but it's pretty challenging. And,
the only TQFT which I know somehow it's Chern-Simons, and it can be described geometrically, yeah, without quantum groups. And here either I'm pretty sure there is.
Yeah, that's right. So that's why I think I'll try to say, I mean, give you alternative definitions of this TQFT. So, I mean, physically, it's clear that it should exist and one can even do computations, but I'm not including any physics here, as you can see in this lectures. So the second question you asked about how it's related to 90s, it's much easier to answer for me. So first I present it as a challenge, but the second question is easier to answer, and I was planning to talk about it later, but let me not keep you in suspense and just do it now. So suppose we consider this unit circle on a Q plane. So this is Q plane. So this object Z hat lives here. So that's where Q is generic inside the unit circle. So you can naturally ask what happens when Q goes to roots of unity, because that's indeed what was studied in the 90s. So far, I already told you about one point on this circle. Namely, I said that here you recover inverse Turaev torsion. but at roots of unity, you can actually recover various other invariants that were introduced and studied in the early 90s, and that was part of the motivation for this work. You can recover Chern-Simons invariants of Witten-Reshetikhin-Turaev. There are non-semisimple analogs, so-called ADO invariants, CGP invariants. There are many of them. Your typical response would be that these are just words because I didn't introduce anything. And in fact, I wasn't planning to speaking about this just yet. But if you, so I have a choice of either give you a quick answer without explaining what this acronym stand for, or not give an answer at all. So I don't know what's best.
No, I don't know. You promise a bigger picture, because if you write a polynomial with 100 coefficients, so I don't know who will be impressed. So like maybe some computer scientists. But if you explain what is a structure, how to obtain it, yeah, but it's up to you.
Well, so far I wanted to be mathematically accurate and just give a definition.
Mathematical accuracy is not just a formal following some logical rules. It's rather a relation between kind of analogies between different theories.
Okay, so let me try to give you more analogies then. Sorry if, again, like I say, there is this conceptual versus concreteness, and I apologize if first two lectures were too concrete or too specific. But again, I wanted to make sure that we know how to compute it, work with this, and before we do conceptual things. So this WRT, ADO, CGP, all of them are associated to quantum groups at roots of unity. And the property of this z-hat is that when you take Q to root of unity and sum over this indices B with appropriate universal coefficients, which don't really depend much on a three manifold, you can reproduce many of these. So that's already a first kind of indication that this object that we constructed has to do with quantum groups at generic Q, because limits reproduce what was done in the 90s. But again, I'll give a little more substance to the statement about quantum groups, hopefully in the next chapter. So for today, I was planning to talk about counting, if it's okay. So in particular, I promised to give you some version of a definition of derived torsion. So that's coming. And in particular, when I speak about counting, so to maybe satisfy part of the request to be more conceptual, I'll talk about counting in three different variants. So first of all, counting in topology. So counting, that's closer to what we were discussing. Then counting in enumerative geometry. And then counting in the context of vertex operator algebras. So this word counting will have several meanings, and it's a big chapter. So it will be maybe more conceptual, but with like fewer theorems or cutting corners, even some more. So first, let me do counting in topology. So Novikov, Sergei Petrovich Novikov, studied the following question. Suppose you have a circle valued Morse function. So this is quite general, but in our case, suppose we have a circle valued Morse function on a three manifold. And we want to count, so that's where the counting comes from. So we want to count gradient flows gradient flow lines of such circle valued Morse function.
For generic Riemannian metric, yeah.
Yep. As usual, in this kind of problem, it will be important that it's generic. If it's not, of course, one would use perturbation. So that's where quite a bit of analysis goes in. But again, this part will be cutting corners more than concrete things, but hopefully will give bigger picture. Morse function. So let me also roll the shared screen. So the result of this clearly depends on the choice of, I'll call it B suggestively by the same name as what we called B before. It's a class in H1 of M3. So we have to specify in which homology class we're trying to do this count. And if our three manifold, remember, since we talked about surgeries, everything is constructed out of knot and link complements. So let's consider K to be just a knot for simplicity. Then H1 is basically Z, and we can say that is generated by X.
Sergei, I must speak on behalf of Sergei Petrovich. No, your S3 minus K is certainly non-compact.
Yeah, that's correct. So at this point,
it's non-compact, you will have many problems with the choice of the Riemannian metric. I'm not sure even how to say what kind of metric, how it behaves near K.
Right, so there are several ways I can answer this question. So first of all, it actually is not so bad. So again, if we spend a little bit more time on analysis, we would see that it's not, this is not an issue. Really, so one can work with non-compact manifold, and that's perfectly fine. In fact, that's what people do. So the theorem I'm going to state in a moment is actually for manifold with boundary. But indeed, one would have to discuss how to perturb the metric. Another quick answer, which is an alternative, since we already learned what surgeries are, you can perform zero surgery on this knot K and basically glue back the solid torus that we excavate when we try to perform the surgery, but we glue it back exchanging longitude and meridian. So in other words, we don't get back the three sphere, but we rather get a closed manifold. It's called zero surgery on a knot. And then same statement I'm going to mention will apply again with small modifications, which are definitely not important for this.
Oh, I am trying to imagine like the gradient line, which kind of asymptotically approach the boundary.
Exactly, you want to remove those. Yeah, that's clear. So that's it will be such things will exist only for very particular choices of metric and Morse function. Yeah. So generically, they disappear. Again, that's a loaded statement. To unpack it, I would have to spend a lot more time. But again, quick way to avoid it is to use the zero surgery with a coefficient P over R that we used before equal to 0. And that will produce closed manifold. What I'm going to say next will hold with, again, small modification, but it will be completely closed manifold. So right, so let's count such primitive closed orbits. Previously we saw, and again, I'll try to be at least somewhat concrete. So previously we saw a couple of examples of knots, so we can do it for some of them. For example, for trefoil, you find the answer of the following form. It's going to be a generating function, and I'll call the variable in this generating function also by x, abusing the notation, but also reminding us that it keeps track of the homology class in H1. So in class -1, we find -1 solution, suitable count with signs. In class 0 will give you 1, that's basically normalization, plus x here. If you do it for k equals for 1 knot, you find minus x inverse plus 3 minus x. And this invariant actually.
What is it? This expression, say x minus 1 plus x, it is answer for what question?
It's the answer for how many. So we have to introduce also signs, which I'm not going to do. I hope it's okay. If you do signed count of such closed orbits in homology class x to the power something.
So I assume that the answer should be an integer number. Not
yes, correct.
Okay.
So integer number is
like 1, 2, 3, 4, 5. So what is x minus 1, 1 minus 1 plus x? Just for the future, you want this integer to represent in this strange way.
Yes. So this is sum over, let me call it b in H1. And we know that H1 is Z, right? So number of closed orbits times x to the power b. So x is a variable for the generating series, and coefficients are the numbers. So, and they indeed have to be integer, you're absolutely right. So they're counting something. Okay. So this count is actually exactly the answer to the question, what is Turaev torsion? So the two questions annihilate each other. So what I wrote here is a Turaev torsion for either complement of the knot K, or if you wish, zero surgery, it's closely related. And a theorem, actually here I'm packing several theorems together, but one of them says that it also has a different name and a slightly different definition. This is also what's known as Alexander polynomial of a knot K. So if you wish, this is a very fun counting definition of the Alexander polynomial, which in most of the encounters in knot theory, you define via skein relations. You say that Alexander polynomial of a crossing of this type minus Alexander polynomial of a crossing of a different type just a second. Is equal to x, let me write 1/2 minus x to the minus 1/2 delta of no crossing. So with the initial condition that delta for the unknot is equal to 1, we can compute it for every knot, and in particular for this trefoil knot, figure 8 knot, and so on. You get, first of all, the answer to this counting problem, but also it shows what the definition of the Turaev torsion is. Again, cutting some corners, no, not through original Turaev's construction, but rather through the Alexander polynomial. So Turaev torsion, if you haven't seen it before, is basically analog of Alexander polynomial, but for closed three manifolds. So that's.
Sergei, can this count be refined geometrically? Number of closed orbits, it's certainly.
I don't know. So that's exactly a good question. So previously I told you that this Q series at hat is counting, is a Q deformation of inverse of Turaev torsion. So first of all, it's I don't know a simple geometric counting problem which gives inverse Turaev torsion. Already at that stage, it's quite challenging. And then, yeah, natural question is how to refine it.
I think that Alexander polynomial can be refined in many ways.
Not in so many ways. For instance, one way you can
in a few ways. Okay, not so many.
No, not so many. First, it can be categorified, but again, we need, first of all, inverse Alexander polynomial. And until recently, this inverse Alexander polynomial, or it's an analog for three manifolds, actually has not been studied either. So that's already first step. Of course, we can stick with Alexander polynomial, but then we get basically Higard-Floer homology, and I don't know any other meaningful deformation.
But many for algebraic knots, yeah, for toric knots, there are more possibilities.
Sure, but they're infinitely, I mean, they have no hope to be TQFT. I mean, to be TQFT, first of all, you need it for any knot and for three manifold. That's extremely strong condition. So therefore, generalizations that could really have any chance to give TQFT, there are basically only one meaningful I know, not Floer homology, and that's it.
Okay.
Of course, we can also change the rank and go to Homfley type story, but again, I don't know if it has any TQFT analog for three manifold. Right. So therefore, this counting discussion or chapter that we're going through right now, what will it do? It will hopefully give you some answers, like, or conceptually indicate what kind of gadget it is, but it will indicate more questions than answers. That's why I didn't want to start with this, because otherwise there would be too many open questions. And now it's easier for me, once we have objects in our hands, to pose these questions rather than start on extremely shaky ground. So that was counting in topology. What about counting in enumerative geometry? So here, there is analogous counting problem, which is roughly counterpart. So hopefully previous bit gives you an idea of what derived torsion is. So now let's talk a little bit about open enumerative invariants. So here, one standard setup is where you start with a pair of X, which is Calabi-Yau threefold. L is Lagrangian set manifold.
Everything will be non-compact, yeah.
Yes. Yeah, for application that we want, everything will be non-compact. And this is actually sometimes not so much a trouble, but rather simplification, as you know well. So for instance, if things are toric, one can quickly use localization type techniques and other things. So in this set of problems, one usually counts either stable maps, but for applications that will need, you can consider embedded curves. I'll call the curve sigma, landing in X and such that boundary lands in L. So therefore, sigma has some genus G, and it has a boundary. So let me call boundary gamma that sits inside L. So here is a picture of what's going on. So if this is our Lagrangian shown in green, then gamma will be a curve in some homology cycle. I'll specify that in a second. And one is typically counting such curves sigma that sit in Calabi-Yau X with boundary on L. So such counting problem depends on various pieces of data. First of all, we have to fix the class. Sorry. a class usually called beta, where the image of sigma is in H2, relative H2 of X with respect to L. This is very standard and is typical for so-called closed counting problems as well. But in the presence of boundaries, we also need to fix the class of gamma. So in the above, I was not precise whether it's a boundary of the curve or image, but here I will be a little bit more accurate. So this lands in H1 of L, and this is actually, again, implementing this in practice for this invariance at head is going to be rather difficult, but this is actually enumerative kind of problem where originally this development came from. So it didn't come necessarily from three manifolds, but came from the study of this open type counting, so-called BPS or enumerative invariants. And
so, yeah, okay, so, super.
And for
it's already application. Because you see, okay, for me this count is not well defined.
I totally agree. Yeah, I totally agree. Yeah. So that's again why I say that this part is maybe conceptually suggesting what interpretation of this coefficient should be, but that's why I know you didn't like long numbers and combinatorial formulae, but that's why I prefer to start with something which was well defined in the first place.
No. It does not mean that it's bad. If it's not well defined, maybe it's good because it's a challenge, as you said.
Yeah. So in fact, like I said, many of these things involving counting will be a challenge because I can indicate from properties what kind of gadget it is. For example, the fact that it gives inverse derived torsion is useful as a statement, but then it suggests how do we deform that by Q, and I don't know. So that's again just a perspective. So this is basically enumerative perspective. So in this enumerative perspective, one takes X to be cotangent bundle to our three manifold. One takes L to be n copies, or rather, I can just write M3 zero section of the above, but with a multiplicity M. And this multiplicity n will correspond to working with SLN or rather GLN. But again, I'll suppress this for a second. So this picture can be useful only for very special M3s, for example, for three sphere or RP3, real projective space, where analysis and enumerative techniques are developed enough to say something useful. In general, I totally agree it's not defined, but one thing that it illustrates is compared to many, maybe other definitions or approaches, is that this counting problem immediately gives you something which is labeled by this labels B. So previously you could ask, it's not entirely natural where they come from, but from such a enumerative count of anything curves ending on Lagrangians, it's clear that generating function of this count surely should be labeled by choice of class of boundary that we call gamma. So in other words, now the statement that I want to make again is that in this way of writing of this that head of M3 and Q as we did previously, so it was Q to some delta B, then it was C0 plus C1 times Q plus and so on. All these integer coefficients, now we see that they have several different meanings or origins. And from this enumerative perspective, they're basically counting such embedded open curves with additional data. So,
so where is it? So this CI is sort of a virtual number of such.
yeah.
Where is the genus?
The genus is Q. So the variable Q is keeping track of the genus. So that's why it's universal for independent on a choice of manifold, but B, from this perspective, naturally is element of H1. So, and there is no beta in this particular Calabi-Yau, so therefore there is no other dependencies.
Very interesting.
Yeah, so in practice, again, there is some work on enumerative invariants, and there is open version of kind of Donaldson-Thomas invariants, or rather there are analogs. This is kind of following Gupta-Kumar-Vafa story and many other developments. One can try to check that, again, for a couple of simple examples, such as RP3 and S3, it's indeed the same object, but making it into mathematical definition, or even computing, even much basic problem, computing it for a few more examples is a big challenge. And I think it's good that it connects to another area. As Jan says, it's not necessarily a bad thing, but it's definitely not as simple as combinatorics that we had before. So that was another reason for me to not start with it. So maybe let me end this lecture with one more counting interpretation of this integer coefficients, the C0, C1, and so on, from yet another point of view. So this is something interesting, again, something that was not expected in the beginning, but then turned out to be the case in every single example. And deep meaning for this is still sort of puzzling, but since it has been verified in every single example, I'll phrase it as a conjecture. So we can call it 3D modularity conjecture. Because in part it sheds light on whether this Q series has interesting modular properties as a function of Q. So conjecture says that if you compute it for 3-manifold as a function of Q, then the result is going to be a character of some logarithmic vertex algebra. I'll call it log VOA, which in general, of course, depends on 3-manifold. And this gives yet another interpretation of this integer coefficients, because what is a character? Character is basically a trace of some module. So V here is module of log VOA. And by definition of vertex algebra, it's graded. So in particular, we take a graded trace with variable Q. So that's the same Q that we used all the time. The grading is provided by object L0. So in VOA community, this is usually called conformal vector. And there is a small correction here, minus C over 24. So this C is called central charge with respect to Virasoro subalgebra of vertex operator algebra. And as a graded trace, it is basically a sum. So I mean, I don't really have to say more. So it's essentially q to some maybe h minus c over 24, and then expansion of the same form, c0 plus c1 and so on, where this c's are basically now dimensions of the graded pieces, dimension of v0 plus q times dimension of v1 and dot dot dot. So this gives yet another interpretation of integer coefficients as graded dimensions of some VOA module. So that's another type of counting or integrality, if you wish, that's happening kind of in the story. So I think we exhausted 1 full hour and even ran a little bit over.
We can continue. It's only started to be interesting. Yeah, especially here, this. So these dimensions are dimensions of some, like informally say, open BPS states.
That's right. So this
factor of Q. Yeah.
Correct. Yes. So therefore, last two enumerative or counting problems tell you that you can think of these coefficients as counting open BPS states, whatever that is. I mean, they're supported on these curves with boundary on a Lagrangian, or equivalently as dimensions of VOA modules. So actually, maybe last one is interesting also because if this conjecture is understood better about this modularity and the relation to vertex algebra, I should make a remark that it provides a nice candidate for categorification of this z-hat. So it basically says that instead of working with graded trace or character, we can just take the module itself and perhaps try to define this module as invariant of a 3-manifold. So that would be pretty cool because it would be essentially the answer to categorification of such invariants.
So this module should be thought according to the general philosophy as a module over closed BPS algebra of this Calabi-Yau 3.
Yeah, combining these two statements, yes, yes.
In particular, your VOA probably can be constructed in terms of this Koha.
Probably because this module depends on choice of, I mean, the module is for open BPS states, but what acts on it, the only thing I can think of is a closed sector. So in that sense, perhaps Koha is the right counterpart, or maybe this VOA has something to do with Koha in this setup. I mean, that's a natural
because as
expectation.
we discussed, there are some examples in slightly different framework, maybe not slightly, where you can derive VOAs from Koha.
Exactly, yeah.
Yeah.
So I think it's indeed extremely analogous to that. So maybe to put in writing, indeed, what this does, where do I have this module here? So I'll scroll down first of all in the screen sharing and write it here, that this module V is basically a space of BPS states, which are open according to the above. And indeed, the most natural action in the enumerative context is by HBPS closed, which is the same as Koha. And this suggests then, so that I don't know. So I'll draw a dotted line to this log VOA, which depends on on a choice of a 3 manifold, or maybe here we don't necessarily need to maybe stay in this context. We could be more general, but in any case, I think it's extremely interesting question. And again, I don't know the answer to this even as a guess or speculation, how to relate this. So it's definitely high level of conjecture, and there should be such dotted line.
Sergei, you had this work with Vyfm4 and with others on VOA associated to 4-dimensional manifolds. I remember M4. And so how this log VOA for M3 is related to that story?
Okay, so yeah, right. So I'll try to explain that part. So maybe I'll do that. So it will take me about 5 minutes. I just want to say for everybody that in some sense, I wanted to reserve extra time beyond 1 hour today for discussion. So that's what I consider now. It's a discussion. And what I'll do tomorrow, one thing I promised you, especially today, is to talk about quantum groups and say how this is FK is defined using quantum groups at generic Q. So I'll come back to quantum groups tomorrow. Of course, you can even ask me questions today, but just as a clearer announcement, what we did not do, I'll finish that tomorrow. Now, regarding the answer to this question about VOA of M4. So what is VOA of M4? So you start with a 4-manifold, and let me call it M4 by analogy. And you also choose a root system, which again will be always implicit to be SL2 for our discussion. And then there is some VOA of M4, which again you can either extract from physics and whatnot. But with Bori, we ask the following question. So suppose you have a 4-manifold which is glued out of 2 pieces. Again, it's a similar to surgery cutting and gluing construction. So in this case, the gluing will be along a 3-manifold. And here there will be M4 plus and M4 minus, two pieces. So in other words, suppose M4 is M4 plus union over M3, M4 minus. So how does this gluing topologically gets realized at the level of vertex algebras? So one way in which, and fairly general, one of the very few ways how it could be very generally is the following, that if VOA of M4 plus and VOA of M4 minus share some common data, namely if the representation category contains as a subcategory what I'll call some modular tensor category associated to M3, then you can consider a natural extension of these 2 vertex algebras, but they have to share something in common. So they have to share some part of their representation theory. So therefore, I don't know how vertex algebra, this log VOA that we saw before for 3-manifold gets related to VOA of 4-manifolds, but it definitely gets related to this MTC of M3. So there is a fairly direct relation between these guys. So that log VOA of M3, and also that depends on the choice of root system, is directly connected to this MTC of M3 that serves as a gluing information between 4-manifold VOAs. But I don't know more direct relation between, I'll draw it in green, between log VOA and this VOA. First of all, they are defined for different conceptually different manifolds. One is 4-manifold, the other is a 3-manifold. You could say, well, suppose we work with 4 manifolds, which are always non-compact, and have M3 as a boundary. Even in that case, I don't know relation, but Bore actually believes that there is a direct relation. So our stands on this are slightly different. And I think that he's probably right, but I don't think I can say too much about it.
This M4 has to be smooth, or can I
Correct.
consider,
Yes.
say,
Yeah.
two coordinate planes C square in C cube, something with intersect over, yeah, so.
In such cases, it probably still can be done, which is very similar to your work, for example, on this subject. But one has to specify what exactly is happening at this intersection. And since you guys do, that's perfectly fine.
No, I'm just curious about this MTC M3.
Well, this MTC M3 arises naturally when you have just, I mean, this M3 is a boundary
MTC,
of
just for you, it's modular tensor category, just in case.
Yeah. I should say that it's MTC, loosely speaking. In general, it's probably just braided tensor category, not more fully tensor category. So I should write BTC maybe, but this is, I guess, less familiar term to most people. Right. Yeah, so here M3 is a common boundary of those pieces. So it doesn't see singularity of a 4-manifold at all.
Mm-hmm.
The dotted line, if Bore is right, probably will see it. But again, I don't know how to uplift the red line to dotted line. That's,
just, but the red line, it's not YM4 plus is kind of, it's related to the glued vertex operator algebra. Why it's dotted line connects log VOM3 only to one of them.
Oh, yeah. So I should probably, yeah, it should connect to both. And just like, yeah, so here the statement is meant to be just like MTC. Actually, let me switch it back if you don't mind. So it's, I'll call it MTC just because I'm used to. So this MTC is only part of representation category for VOA M4 plus modules and VOA of M4 minus modules, right? It's a small part of that representation category. Similarly, one can expect that log VOA of M3 sits inside VOA of M4 plus and M4 minus as some small subalgebra or something. And again, it's probably right. I don't know if in what sense this is true or how to make it precise. In examples, it seems to be, I mean, many of them are very close, especially if we play with, remember in the beginning, you were suggesting, let's do linking diagram, for example, for this plumbing graph and so on. In those cases, it will almost coincide, which is, in my opinion, deceptively simple, but it's probably a hint that this is true in general. Yeah.
I recall in this world of VOAs, there is something called conformal extension.
That's exactly it, yeah.
It's what's happening.
Yeah, so if you want to glue two VOAs along, or two manifolds along common boundary, you do exactly this conformal extension, but that needs to be done with respect to some set of modules. And how you pick those modules, that's exactly what MTC of M3 does for you.
Mm-hmm.
So they have to share, in other words, two VOAs. You cannot just do glue meaningfully to random VOAs. I mean, there is no way to do it. But if they share some part of their modular data, then there is a way to do it. And that's exactly this conformal extension.
Interesting. Yeah. Good. So since it's a discussion, more questions?
Yes, could you say anything how you have this M4 plus, VOA M4 plus and VOA M4 minus? They shared this MTC M3. How is this relating with the VOA M4?
namely on the diagram, the blue lines, these lines, or the green or the red ones?
No, there was VOAM4, and Zhongzhu is asking how these two things. So, is it true that VOAM4 is just this conformal extension of these two pieces?
Yes, that's exactly right. Yeah, that's correct. Yeah. Does this answer the question? Or, I mean, again, there are many details in this paper with Fagan, but basically that's the answer. Yeah.
I try to say that so the representation category of M4 is the conformal extension of those two M4 plus monaces, or
Yes. Yeah.
Mhm.
Yeah.
And
Yeah.
do you have any guess what the red line, the log VOM3 relating with the MTC4, is that the fusion category of this?
Basically, yes. So that's like I say, there is a lot. I mean, this red line is much better understood than the dotted green line. So that's why I put the red line as a solid line and then dotted something that, again, maybe it's a level of observations and so on. But here, the connection, there is some discussion of it in the paper called 3D modularity. So it's again related to that conjecture above, and the MTC of M3, the way it appears on this. So since you asked, maybe let me try to make a little bit more precise statement. So we can consider representation category of this log VOA of M3. So I'm going to erase this for a second. So log VOA of M3, and we're going to consider its analog of MTC. It's not quite MTC bits because it's logarithmic. So we will consider category of its modules, but it has structure which is very close to MTC. And then it's also going to be huge. It's going to be very, very big. But this MTC of M3 sits here, first of all, and it seems that it's related to semi-simplification of this category on the left. So that's perhaps the best statement I can say without going too much into details.
I see. So the log VOA, which somehow corresponding to the representation category of a quantum group at roots of units, and the MTC, which is only giving this, you see the fusion category from the tilting module, which is
yeah, right. So
and I just kind of take the analogy of in that sense.
Well, to make sure I understood, so this log VOA here may or may not be related to quantum groups at roots of unity, where you find non-semisimple tensor categories associated to this, because notice that our log VOA is labeled by 3 manifolds. So there are zillions of 3 manifolds, and for example, as many as this plumbing graphs, and that's already way too many. Whereas UQ, I mean, for example, if you take restricted quantum group or some other form, yes, we will find some logarithmic tensor category associated to it, but it's not labeled by as rich data as enters up there. So only in some special cases. I mean, there are indeed relations.
That's what I was comparing the special cases. And inside you don't have a small MTC of the restrict the tilting modules.
Yeah, in those cases, actually, these are the ones which are associated exactly to this thinking diagrams that you and Jan were asking in the beginning. and namely 3-manifold itself somehow knows something about the root system. So it's interesting that in the end, we're going to discover exactly, I mean, this log Vyfm4 for those 3 manifolds, which are defined by root systems. They're basically link of AD singularity, surface singularity. So those are going to be indeed related to non-semisimple tensor categories for quantum groups at roots of unity. I didn't want to mention this because it's a little bit confusing, because in the whole story that I was discussing, quantum group at generic Q is more relevant, but this is very interesting duality where somewhat unexpected connection to also to roots of unity shows up without us taking Q to root of unity. This is like characters. So character for some 3-manifold at generic Q happens to be character of log VOA associated to root of unity. Yeah.
Okay, thank you.
Sergei, and this integral formulas which appeared previously, is it the way to, I mean, do they have interpretation in either of these enumerative realizations of the count?
Only partly. So again, I apologize if I didn't start with the enumerative story first, but it came, I mean, this integral formula came from another aspect of the story, which is much more physical. So that's why I wouldn't be able to explain it. It's goes by the name of this 3D correspondence. And I don't know how to write these integrals in other incarnations, for example, in terms of enumerative geometry or Koha. So, I mean, if you have ideas, I would be delighted to hear.
Well,
it would be
if I knew what is a 3D to 3D, so I know that there are some 3-dimensional gauge theories, but now I should be very careful because I'm not sure what is the number of supersymmetries you are talking about. I know this Coulomb branches story 3D n equal 4 and symplectic duality better than, say, 3D n equal 2. So what 3D to 3D, what kind of, is it something different?
It's different, but not too different. So in that sense, I think you would perfectly understand at least the sequence of operations in that language. But what I meant is that we can just take the output of this 3D correspondence, which are exactly these integrals. So I presented to you these integrals as a definition, so they basically come kind of out of the blue.
Functions.
Yeah. Right, but then question is, once we already have the answer, can we interpret them in terms of Koha or enumerative story? That's what I meant. And I still don't know how to do it without even thinking, I mean, treating 3D as a black box, which spits out this as an output. I think it would be still a great project to interpret this output in these other terms.
Yeah, we can discuss it somehow separately. Yeah, more questions? Okay, so if there are no more questions, so there will be last lecture of Sergei tomorrow, and the time will be different from today's. It will be same as in the previous 2 lectures, which is 1:30 p.m. local time. I mean, local Kansas time, because I see here people from different areas of the globe, actually. Yeah. Okay. So if there are no more questions, so thank you, Sergei. Very, very interesting. Okay. Thank you.
Yeah, if you